Welcome to Frank Stajano Explains. Today's topic, since we are still in exam season, is once again an exam question walkthrough of a discrete mathematics question set by one of my esteemed predecessors. Now, I very much hope that these walkthroughs are helpful to you in preparing for the forthcoming exam. And if they are, please be sure to stick a like on the video, either straight away or when you come back after having done the question on your own. But as I said at the times, you only get the maximum benefit from these videos if you watch the rest after having attempted the question on your own as seriously as if this were a real exam, as I explained in the 3 secrets video. So I'll pause now. Please do the question by yourself, then come back, and then stick a like on it. Stop the video and do the question by yourself. Alright, welcome back. Let's have a look at this question. This question is rather long, and I can see I get credit for doing 7 different things. So I better check first. I've only got half an hour, so I should make sure that I don't run out of time. I should give it a first pass and maybe then refine later. So the first 5 things are about a language over an alphabet of just 2 symbols A and B, where we have a primitive number x of w, the number of occurrences of the symbol x in the string w. And for each of the following 5 languages, L1, L2, L3, L4, L5, determine with justification whether or not the language is regular. Alright. L1 is the language made of strings in sigma star that have the same number of A's as of B's. That sounds like the kind of stuff that is not regular for the classic pumping lemma argument that if I had to take into account whether there's as many A's as there are B's, I would have to somehow remember how many A's I have seen, because I may see a bunch of A's before I even start seeing the B's, and to check that there's enough B's, I have to know how many A's I have seen, and to remember an arbitrarily large number of A's, I would need to have an arbitrarily large number of states in my DFA. And so with the pumping lemma I can technically show that this would not be a regular language. So at 1 I know how to do, and the answer would be no, it's not regular. This L1, W is in sigma star such that W has an equal number of occurrences of the substring AB and BA. So at first glance this looks like the same, because I treat AB as a kind of super symbol and BA as another kind of super symbol, and it looks like I could use the same idea, that if I have to remember how many times I've seen AB, then I would need a number of states that's large enough to accommodate arbitrarily many ABs, so that I can count them off with the BAs and see if there's the same number. So that would indicate that this is also not a regular language for the same reason. L3, inductively defined by the following axiom and rule, and the empty string is in the language, and then if a string's in the language, then something where you put an A in front and a B at the back is also in the language. And this looks very suspiciously like nested brackets, if you consider A as the open bracket and B the closed bracket, which we know we cannot recognize with a regular language, with the DFA, because of yet the same reason that I'd have to count how many brackets I've opened before I see if there's the same number of brackets that close it. And so this again looks like not a regular language, for more or less the same reason once more. Number 4, inductively defined by the following axiom and rules. Empty strings in there, then U. If I have U, then UB does the same rule as before. But I also have 2 more rules, which is if I have a string in the language, then I can add an A in front. If I have a string in the language, I can add a B at the back. So that seems more liberal than this one, because I can have strings that don't have the same number of A's and B's. These ones definitely had the same number of A's as B's, plus the extra constraint, all the A's were at the front. Here, I don't have that constraint on the having the same number of A's and B's, but I do have the constraint that all the A's come at the front of the string and all the B's at the end. I can easily convince myself that all the strings in this language, if they have any B's, they are at the end. And if they have any A's, they are at the front. So this does actually look like a regular language. Basically all the strings made of A's and B's, where if you have any A's, they're on the front, and if you have any B's, they're on the back. And that seems to be something I can easily recognize with a regexp of the type A star, B star. So that should be an easy yes. It's the first yes we've seen so far in this first pass. And then it's L5. The string such as the number of A's is equal to 3i, and the number of B's is equal to 7j for some I and j, which are natural numbers. This seems like a fancy way of saying that the number of A's is a multiple of 3 and the number of B's is a multiple of 7. This looks like a regular language which I can recognize with a DFA that had a cycle. Yeah, I'd need to kind of nest 2 cycles, but yeah, I can see how this would be a regular language if I only had the first part, if I only had this part, then I would make myself a DFA that goes like this. And this is basically 0, 1, or 2 A's. If I get an A, I go here. Like this, and I start here, and this is an accepting state. And if I get 0 A's, then it's good. If I get 1 A, if I get 0 A's, it's good. If I get 1 A, that's no good. If I get 2 A's, that's no good. But if I get 3 A's, it's good. If I get 4 A's, no good, and so on and so on. And I cycle here. And so that if this were the only rule, then that's an easy way of doing that. And if I have this other rule as well, then I can do a 2-dimensional version of this, where in this direction I have the 7 B's. I have 0, 1, 2, 3, 4, 5, 6, and then come back here for B's. And I repeat that for every one of these. So I basically have layers of these, and a 2-dimensional DFA, where the only accepting state is this 0 for both dimensions. And so I can see how I can say, yes, this is a regular language, and I can recognize it with a machine I know how to build. Consider the set R of all regular expressions over the alphabet A and B. Give an alphabet sufficient to express any element of R. Well, that seems trivial bookwork. I just have A and B, and then the meta symbols that are necessary for making the regular expression, which is the brackets and the star and the or sign, and the epsilon for the empty string, and the phi for the anti-regular expression. And that's it, and easily gained 2 marks. And then state, giving reasons, whether R is a regular language. What's R? R is the set of all regular expressions over the alphabet AB. Is R a regular language? So is there a DFA that will recognize whether a string of these of symbols in this alphabet I built in the previous sub-question is a valid regular expression over this alphabet? And by the fact that there are brackets and the brackets have to be balanced, the answer would be an easy no, because I can't balance the brackets with the DFA for the same pumping lemma argument that we've already used several times already. So that's my first pass, and in about 10 minutes I managed to convince myself I could give an answer to one of these, and I should now revisit to see where I should give a little more justification, or maybe if I made a mistake. Alright, we've done our first pass. Let's now do a second pass in detail, safe in the knowledge that we more or less have some plausible answers to all the questions, but we may want 4 maximum marks to refine those justifications and perhaps discover if we've been too quick in giving some answers off the cuff. So first of all, for this one, number of A's is equal to number of B's, and we said no, it's not regular because a DFA is only going to have a finite number of states, and we are never going to be able to recognize an arbitrarily large number of A's so that we can remember if I had seen that many when I have to compare with the number of B's. So the formal way to say no in this case is by using the pumping lemma. The pumping lemma tells us we have if a language is regular, then it will enjoy this pumping lemma property, which means that beyond a certain size of string, all the strings are pumpable. And so to prove that the language is not regular, it suffices to say there is a whatever number n that might be, I think it's called L, whatever number L for the length from which onwards all strings are pumpable. You give me any L you like, and I will show you at least one string that is in this language but isn't pumpable, in the sense that if you pump it, you obtain strings that are not in the language. So that's how I use the pumping lemma to show that the language cannot possibly be regular. I don't pretend to know what L is, but I'll show you that for any L you might care to give me, I'll find you at least one string which is not pumpable. So give me any L, and I'll show you. So you have this L. Maybe I want to shrink this so I have a little more space for my own drawings. Okay, shrink this. Get rid of this. I don't know how this appeared. Okay, and right for this one. So you give me an L. Okay, and I'll show you that for your arbitrary L, I can find you a string that cannot be pumped, and that string is going to be made of ALs followed by BLs. This is a classic, okay? And this string cannot be pumped because pumping the string means taking something, an initial prefix of the string of length not greater than L, and splitting it into two parts, U and V traditionally called, the second of which, the V of which cannot be empty, and then raising the V to arbitrary powers, natural number powers, and then that's the pumping action. And we should, if we do that, then the resulting string is not in the language L1. So if I take an initial substring of length L, then it will only be made of A's, and so my U and V, however I split U and V with a non-empty V, is going to have a V that's made of some number of A's. Let's say U is U equals A to the K, and V equals A to the L minus K, obviously. Now if I raise this thing to arbitrary powers, I'm immediately going to unbalance this string, because it's going to be made of A to the K and then some other number of A's. Even if I raise it to the 0, then it's going to be an empty one, and this K is going to be different from L, and so this is going to be unbalanced. And so I've shown that for any L I can find you a string that is not pumpable. If you were to pump it, then you would obtain things not in L1. So that's okay. This one is not regular, and I have given you a rather detailed proof using the pumping lemma, and I'm sure I would claim my 3 marks by that. Now L2. L2, an equal number of occurrences of substrings AB and BA. And I said I was going to use the same argument. How would I go about doing this with a substring? And because when I construct this, I'd have to, if I want to do the formal thing with the pumping lemma. But actually, the more I look at this and the more suspicious I am, first because there were too many things that would have used the pumping lemma. So we'd have this one, then this one, then this one, and this one. That's somehow few too many for the same question. So I'm suspicious there's something more to it. And as I look at it, I see, well, substrings A, B, and BA, nothing says that they have to be treated as separate symbols, because they could actually overlap. So if I consider a string such as ABA, so how many occurrences of the substring AB are there in here? Well, there's one. How many occurrences of the substring BA? Well, there's one. But I couldn't treat them as, you know, the symbol AB and the symbol BA, because if I treat this as a symbol AB, then there's no more BA. So because nothing in the question says that these occurrences of these substrings are distinct and separated, if I read it as it's written, number of occurrences of the substrings AB equal to the number of occurrences of the strings BA, then the more I read it and the more I convince myself that actually this overlap is allowed. And so if I have something that says AB, 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 AA, BB, then the number of ABs would be, I have an AB, an AB, an AB, and an AB. The number of BAs would be the BA I have here, the BA I have here, BA I have here, and that's it. So I would have 4 ABs and 3 BAs, and I would say this one is not in the language. Now, if I look at it with this understanding, then it's a rather different problem than the one where I was considering AB a symbol and BA a symbol, and I'm not so sure anymore that it is not regular, because actually this A and B, consider A and B as the two levels, like high and low, or 0 and 1, or what happened to this? So A and B are like levels, and I'm A, B, A, B, A, B, A, B, B, something like a kind of square wave signal like that. Then AB is just these up edges, and BA is just the down edges. So if I view it this way, then I have 1, 2, 3, 4 rising edges and 3 falling edges. And so the number is not the same. And I have the same number of rising edges as falling edges if I end up at the same logic level, so to say, where I started. So if I start with A and finish with A, then I have something with an equal number of occurrences of substrings A, B, and BA. Or if I start with B and then zigzag and then finish with B, then I've had the same number of BAs as I had of ABs. And so I think that should be a regular language, and in fact I can recognize it pretty easily with something like, okay, I start, if I make myself a DFA, I start here, and if I get an A, then if I then get another A, it doesn't matter. But if I get a B, and I get into a stage where I can count whether I am getting, so this would be the AB, and this would be the BA. If I have as many ABs as I get BAs, I end up in this state, which I make accepting. And if I have one more AB than I have BAs, then I end up in this state, which I make non-accepting. And similarly, if I start with a B, I can either have A goes here, so this is A, and BA stay here. If I get more Bs, I stay here. But if I get an A, I go into this state, and if I get a B, I go back into this state, and then this one's accepting. And if I get any more A's, I stay here. And actually, if I start here and I don't get anything, then this is also accepting, because I have the same number of ABs as BAs, which is none. And so this state is also a non-accepting state, and these 3 ones over here are accepting states, and I've made myself a DFA that accepts all and only the strings with the same number of AB transitions as BA transitions, or same number of BA transitions as AB transitions. So this one, I take back what I said when I was considering these things as separate symbols, which I don't believe is the right thing to do, because from the way the question is written they could be overlapping, and I say this one is regular. Proof of that being the DFA that I just built. Now the third language, inductively defined by the following axiom and rule, A and B. That's again the one with nested brackets, and I can use exactly the same reasoning as the first answer to say that it is not regular. I can use the same example. A to the L, B to the L would be a string that is in L3, but also a string that is not pumpable. Any L you give me, A to the L, B to the L, is in the language, but if you try to pump it, then the result of the pumping will not be in L3, and therefore this one is not regular, and I've given you a justification. And then L4, inductively defined by the following axiom and rules. And this one we already said as we were going through. I think needs no more justification than saying that this language is basically recognized by the regexp A star, B star, where first I get all the A's. A's are always on the left and B's are always on the right, but I have no need to match number of A's to number of B's, and so because this regexp exists, then L4 is a regular language. So the only thing I haven't quite formally done is to prove that this regexp is equivalent to these inductive rules, but I won't bother with it. So this one is regular. I won't bother with it in the economy of how many things I have to do for 20 marks in 30 minutes. What else is there? L5. This one I basically already told you my strategy for doing it. I can finish this off by completing this DFA. I would have another one here. Let's go this. Well, let me make this bigger because we can't really see what I'm doing otherwise. So if I call this 0A, 1A, and 2A, and I call this 1B, 2B, 3B, 6B. And then, okay, well, I'd have to come up with other names for these other things. I will refrain from naming those other blobs. But the point is that I go with B, I go into here, with B, I go into here, B, 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 and this last one goes here, and these ones go here with B's, B, 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 and come back here, and this one, this one comes back here with a B, goes down here with the other B's. You see what I'm doing? And then with the A's you go across like that. Come back. A. Well, this is getting a mess, but I think that the intention is clear, and the only accepting state is going to be this one here, which is the one where you have, so basically these columns, you have a transition between any state in this column, any state this other column by moving with B, with A's. If you are anywhere here and you get an A, you go to the corresponding one in this column. If you get another A, you go to the corresponding one in this column. And you get another A, you go to the corresponding one in this column, at which point your number of A's is divisible by 3. And the same thing with the rows. Anytime you get a B, you get to the next row and then you wrap around. And the only time that your number of b's is divisible by 7 is if you're in this row. So you only have a number of a's divisible by 3 and a number of b's divisible by 7 when you are in this state, which is the initial state and also the only accepting state of this DFA. And that concludes my proof that this is indeed a regular language. So this is regular. And then give an alphabet sufficient to express any element of R. This one I've already done. It's AB plus the 6 meta symbols. And then state giving reasons whether R is a regular language. I think I already did whatever I needed to do, which is to say, well, this R includes brackets, and the brackets have to be balanced, and therefore this cannot be something I can keep track of with a DFA for the usual counting argument, which I can formalize with pumping them in the same way as I have done here. I could make give me any L, and I will give you the string this to the L and that to the L, and with the same development. Then you can pump any initial section here, and then the number of open brackets will now match the number of closed brackets. And that's it. 20 marks in the bag. And as always, if this video was useful to you, I'd be really grateful if you stick a like on it and make the button turn blue. Thank you very much, and best wishes for your exams.